Okay, great. Welcome back. This is part 4 of the radiation and heat transfer type part of the lecture here in Energy 301. We really only have two things left to talk about in this part of the lecture here. What determines the amount of shortwave down that we're receiving from the sun, and what determines the amount of long wave down that comes from like the sky and greenhouse gases and clouds and so on. We're going to focus on that first one there because that first one in this part of this lecture here is going to be about shortwave radiation. What determines the amount of shortwave radiation we receive from the sun? That, of course, will determine things like how much power your solar cells can produce. That's going to determine the amount of heat being gained by the surface during the day, all of which has lots of implications for electrical load and yield. And the somewhat scary term that we use to describe this is Earth-Sun geometry. The amount of shortwave radiation that we receive from the sun, that is shortwave down, is going to depend on both the noon sun angle, how high in the sky the sun is on a given day, and the length of daylight, how long the sun is up on a given day. And both of these are going to end up determining on the latitude and being determined by the latitude and the day of the year that we're talking about here. Now, the sun angle has to do with how high in the sky the sun is going to get on any given day. And you probably know that if you live in the northern hemisphere, during the summer the sun gets very high in the sky, and during the winter it isn't particularly high in the sky. We're going to be computing noon sun angles in a little bit, but noon sun angles are going to have a lot to do with like the angles that you're going to want to position solar panels, so that you can generate power most efficiently. From the point of view of meteorology, the importance of noon sun angle has to do with determining shortwave down in the sense of the sun angle and how it changes the beam spreading. Now, we're going to wait till later in the semester to actually mathematically define the beam spreading, but just to give you a sense here, see on the left there that kind of tropical scene? That tropical scene there, the sun is almost directly overhead, and the rays of sunlight, each beam of sunlight is covering each 1 unit wide beam of sunlight is just warming a 1 unit wide area on the ground. In contrast, over there on the right, the igloo there, when the sun is very low on the horizon, the shadows are long, the beams are spread over a much larger area, and so like in that case, a 1 unit wide beam of sunlight has to warm up a 2 unit wide area on the ground. The beams have been more spread. We'll deal with the math of that later. But this business of how the sun's angles depend on latitude is a little hard to picture until you think about what the Earth, the rays of the sun that reach the Earth are basically parallel. Yet every latitude is going to be experiencing a slightly different noon sun angle and a different amount of beam spreading. I mean, look at the guy up there near the North Pole. From his point of view, the sun is on the horizon. In this particular picture here, that person that's just south of the equator there, from his point of view, the sun is directly overhead. For persons in the northern hemisphere, they're looking south to see the sun. People in the southern hemisphere are looking north to see the sun. This is a complicated issue of Earth-Sun geometry. And to understand why it works that way, you need to first remember that the Earth's orbit is this huge ellipse around the sun, where the sun is not actually quite in the center of it. It's at a location off to one side of the center of the ellipse. The right word for the position of the sun is that it's at the focus of the Earth's orbit. And this huge ellipse means that the Earth is sometimes closer to the sun and sometimes farther from the sun. The Earth is closest to the sun on a day that's called perihelion. And perihelion, para, around, helion, the sun. Perihelion tends to occur right around January 4th, and on that day the sun is about 91.4 million miles away. In contrast, the Earth is farthest from the sun on a day called aphelion, A as in without, helion, the sun. It's the day that we are farthest from the sun, and it works out to about 94.5 million miles away. This difference does not produce a meaningful difference in like the temperature of the Earth. I mean, it's a big difference, right? The sun is the Earth is literally like 3 million miles farther from the sun in July than it is in January, but keep in mind that's relatively small compared to the total distance that the Earth is from the sun. It doesn't make a meaningful difference to the temperature of the Earth. It doesn't make a meaningful difference in terms of like how much power a solar panel is going to be able to produce or whatever. This changing difference is not responsible for the seasons. This changing difference is not responsible for different amounts of power being produced by your solar panels. What is going to matter is the tilt of the Earth's axis. The Earth is tilted on its axis 23.5 degrees from vertical, from the plane of the ecliptic, to use the correct term. It happens to be pointing in the direction of the North Star Polaris, and this tilt is constant. The Earth is always tilted off into the same direction in space. It's simply because there's nothing pushing the Earth to change. Once the Earth, due to collisions or interaction with the gravitational fields of other planets or whatever, once the Earth reached at an angle of 23.5 degrees, nothing has been there to push it to be at any other angle. And as the Earth goes around the Sun, that tilt of the Earth's axis is going to result in changes in the length of daylight for different locations, changes in the amount of, noon-sun angle for different locations, and therefore going to set up changes in the amount of shortwave radiation being received by the surface, and ultimately changes in like the seasons and so on. For example, let's take a look at what the Earth looks like as configured on the June solstice. Now on the June solstice, June 21st, the Sun is going to be directly overhead for locations that are at 23.5 degrees north. That actually has an important name. That's called the Tropic of Capricorn. Notice that, picture the Earth, if this were animated, you could see the Earth spinning there. Notice that the North Pole, and in fact everything north of the Arctic Circle, is in 24 hours of daylight. As the Earth turns on its axis there, the North Pole never gets into the side of the Earth that is shaded. And notice that the same way, at the South Pole and everything south of the Antarctic Circle, you're in 24 hours of darkness. As the Earth turns on its axis, you're not going to, that location will never be facing the lit side of the globe there. The length of daylight for locations at the equator is going to be 12 hours, but the farther north you go, the length of daylight is going to get longer and longer. The easiest way to think about this is to realize that the length of daylight is actually always going to be 12 hours of daylight at the equator. Now at the June solstice, where at the North Pole they're getting 24 hours of sunlight, then think about it as you get north of the equator in June, the farther north you get, the longer and longer the days get. It's an amazing phenomenon, actually. I often spend my summers working at a research institute at the University of Cologne in Germany. Cologne's pretty far north, I don't know, 50-some degrees north. Oh my goodness, in June, the sun's still up at like 10 o'clock at night, and it's up again at like 4 in the morning. It's pretty cool that you can still be out getting a cup of coffee or a beer or something at 10 o'clock at night and it's still light, but you're not so crazy about the fact that at 4 o'clock in the morning the birds are singing. Well, yeah, but they're getting like 18 hours of sunlight at that high north latitude in the middle of the summer. So the farther north you go, the longer the lengths of daylight are going to be getting. On the June solstice, June 21st, only the people at the Tropic of Cancer, 23.5 degrees north, are going to have the sun directly overhead. That's an important term. That means that 23.5 degrees north is the solar declination on that day. On any given day, there's a location on the Earth called the solar declination. On any given day, the solar declination is the latitude at which the noon-sun angle is 90 degrees, because the sun will be directly overhead. The solar declination is 23.5 degrees north on the June solstice. The sun angle will be highest at the solar declination, it'll be 90 degrees, and then it will be, the sun angle will get lower and lower the farther you get away from the solar declination on any given day. Let's change it, kind of mix this up by looking at the December solstice. Notice that on this diagram here I have of the December solstice, the North Pole is in 24 hours of darkness. If you could imagine animating that globe as it was turning there, the North Pole would never be on the daylight side of the globe. In fact, neither would anything north of the Arctic Circle. In contrast, notice that the South Pole and everything south of the Antarctic Circle is in 24 hours of daylight. As the Earth turns, those places are never on the dark side. On that day, on the December 21st, the December solstice, the solar declination is at 23.5 degrees south, a location that has an important name. It's the Tropic of Capricorn. Now again, the length of daylight is always 12 hours at the equator, so as you get south of the equator, the length of daylight gets longer and longer, and you get to days that are like, until eventually you get to daylight that's 24 hours long. Meanwhile, in the northern hemisphere, the farther away you get from the equator, the shorter and shorter the days get until you get to the Arctic Circle, where the length of daylight is 0. So this is why the length of daylight gets shorter and shorter in the winter the farther north you go. Again, thinking of my experiences in Germany, in November and December, when the length of daylight is very short, the sun might set by 4 o'clock in the afternoon and not come up until 10 o'clock in the morning. I mean, you have it's really dark at those latitudes in the winter. Only people on the December solstice, only people at 23.5 degrees south, the Tropic of Capricorn, are going to have the sun directly overhead at noon that day. So we would say that the solar declination on December 21st is at 23.5 degrees north, 23.5 degrees south. The sun is therefore highest at that location, and therefore there is the least beam spreading at 23.5 degrees south on December 21st. And in the northern hemisphere, the sun angles will be relatively low, and this is going to be winter. The days are short and the sun is low in the horizon, which means that we're going to have relatively large amounts of beam spreading. The noon sun angles are going to be low. Let's think about what this means about this business of the solar declination. Remember, the solar declination is the latitude at which the sun will be directly overhead at some given day. The farthest north it can ever be is 23.5 degrees north, and the farthest south it can ever be is 23.5 degrees south, and every other day it'll be someplace in between, like on the March equinox, which is roughly March 21st. Then the sun is going to be directly overhead at the equator. The solar declination will be 0 degrees, and the length of daylight will be exactly 12 hours everywhere, hence the word equinox, equal night. On the equinox, every place on Earth has 12 hours of daylight and 12 hours of darkness. So you can see that this business of being able to figure out the solar declination, the latitude at which the sun is directly overhead, will be important. We have a chart, there's equations to compute the solar declination, but an easier way to do it is with a diagram called the Analemma. And here's a copy of the Analemma. I'm also making a copy of it available to you on Blue Line, because you might need it for some problems that we'll be solving. The Analemma is a chart that's used to compute the solar declination on any given day of the year. And the Analemma is basically just a big calendar. You kind of follow it along the edge there, and you look at the dates on there, and when you find the date that you're looking for, just read over to the y-axis to be able to figure out what the solar declination is. So like on this example here, if we were saying May 15th. On May 15th, then you would read across and you would find out that the solar declination is, something like 18.5 degrees north. Don't worry about what it says. I was just reusing a slide there. You know, and have a quiz about this right now. You need the solar declination if you're going to actually compute the Newton sun angle. And there's a simple little word equation that we can use. Now, this semester is going to have lots of very quantitative things with equations and so on. But for now, I just want to use a simple word equation here to describe sun angle. I want to say that the noon sun angle is going to be 90 degrees minus the distance between your latitude and the solar declination. This is a very simple little word equation. Let me just sort of do an example here. Let's find the noon sun angle in Omaha on September 22nd. Okay, there's a couple steps we're going to follow here. First, ask yourself, what is the solar declination on September 22nd? There's a number of ways you can answer that. You could remember, hey, September 22nd is the September equinox, therefore the solar declination is at the equator, 0 degrees north. Or you could use the Analemma and go around the little graph and find where September 22nd is on that chart and read across and see that the solar declination is 0 degrees north, whatever, however it works. Step 2, find the distance between you and the solar declination. Well, in this problem, Omaha is at 40 degrees north, the solar declination is at 0 degrees north, so the distance between 40 and 0 is 40 degrees. And then finally in step 3, you're going to want to find the sun angle. So you're going to say 90 minus that distance. 90 minus 40 is 50. Therefore, at noon on September 22nd in Omaha, the sun will be 50 degrees above the horizon. How high is that? You know, if you can picture a 45-degree angle, 50 is just a little bit more than that. The sun is only 50 degrees above the horizon on September 22nd. Let's do the same sort of thing for December 21st as another example. So we're going to find the noon sun angle in Omaha at 40 degrees north on December 21st. Step 1, ask yourself, where's the solar declination on December 21st? Well, you could remember that December 21st is the December solstice, therefore the solar declination is at 23.5 degrees south, that is the Tropic of Capricorn. Or you could use the Analemma and go around the edge there and read across that find December 21st and look across and see that the solar declination is 23.5 degrees south, whatever. Okay? Step 2, find the distance between your latitude and the solar declination. Okay, in this problem, our latitude is Omaha, which is 40 degrees north. The solar declination is 23.5 degrees south. The distance between 40 north and 23.5 south is 63.5 degrees, because you go from the 40 north down to the equator, and then from the equator down to 23.5 degrees south. So 63.5 degrees is the distance between your latitude and the solar declination. That leads us to step 3, which is figuring out the sun angle. 90 minus that distance. 90 minus 63.5 is 26.5 degrees. Therefore, on December 21st in Omaha, the sun will only get at noon 26.5 degrees above the horizon. That's not very high at all. The day will be very short. In Omaha on December 21st, I looked it up, and I think there's like 9 hours and 15 minutes of sunlight. And when the sun is up, it's not very high above the horizon, so there's a lot of beam spreading. No wonder it's winter in Omaha in December, where there's very little shortwave down. There's also very little chance to produce power using solar cells, because the total amount of sunlight just isn't going to be all that great. Now, before we move on, I want to actually have you try to do an example of these kind of calculations, and I recognize that this is your first exposure to this and you might have some trouble, but let's just call this question 4. And I'm going to say, what is the noon sun angle at 45 degrees north on April 20th? All right, you can actually get April 20th off of this chart that I have here on this diagram, or you can go ahead and print the Analemma or whatever, but try to compute the noon sun angle on 45 degrees north on April 20th, and choose for one of these. Follow the link on the video below this video to get some feedback before you move on to the final part 5 of this lecture.